To finish off this section and the chapter, for that matter, we are going to look at integration in spherical coordinates. So we've already discussed how spherical coordinates work. Now we're going to talk about how to integrate within this new coordinate system. Now the first thing I want to remind you of is that we've had to calculate our dv differently depending on which of the coordinate systems we're in. In rectangular, dv was simply dx, dy, dz. In cylindrical coordinates, dv was dz, r, dr, d theta. And now, in spherical coordinates, we need to discuss what that volume increment will be. So of course, in spherical coordinates, we are not going to use rectangular boxes. Instead, we're going to come up with something like a spherical box, and we see that here in orange. The spherical box is made up of 4 polar rectangles, one on each side, and then the top and bottom of the box are little pieces of a sphere. So to calculate the volume of a spherical box, we are going to take a factor of d rho, so that's giving us the distance along this edge of the box. So we have our d rho factor. We also need rho d phi. Rho d phi is giving us the arc length of this side of our box. And then we have one other side to multiply by, and that's the factor of rho sine phi d theta. And that is coming from the area of the polar rectangles. Sorry, lots of us there. My apologies. So with our volume calculation, we can write our dv, our volume increment. Notice that there's 2 factors of rho, so we'll have rho squared. We have a sine phi, and then d rho, d phi, d theta. So anytime we're integrating in spherical coordinates, our volume increment would become rho squared, sine phi, d rho, d phi, d theta. And one of the best parts about integrating in spherical is that most of the surfaces that we will integrate are just equal to constants. So rho equal to a constant, that gives us an entire sphere. Phi equal to a constant, that gives us a cone. Theta equal to a constant, well, that gives us a plane. That one's kind of boring. But either way, most of the equations that we integrate are going to be very simple, just constants, but you'll still have what looks like a function to integrate because of this volume increment. So for example, I have a triple integral already set up over here. Now, sometimes the volume increment will not be there. So this same problem could have been presented to you without this stuff in here, and instead just saying dv, and then you would have to know to replace the dv with the appropriate volume increment for spherical. And to evaluate this integral, we're just going to work our way from the inside out. Same thing we did in cylindrical, same thing we did in rectangular. So let's go for it. So our final answer for this triple integral in spherical coordinates is 2 pi over 3. Notice that because a lot of this was just straightforward polynomials or trig functions, our integration techniques were pretty simple and straightforward, and that's kind of the best part about working in spherical coordinates. The hard part about working in spherical coordinates is getting used to looking at equations and recognizing what the surfaces are. Now sometimes the problem will start off with equations in rectangular coordinates, and we have to translate them into spherical coordinates, and that's what we're working with right now. So we want to set up an integral for the volume of a region bounded by a cone and a hemisphere. I have the cone plotted. Let's pull that up. I have the hemisphere plotted, and then I went ahead and merged those together so that we could see exactly what the region is that we're trying to find the volume of. So that's the third picture. We want the volume of this thing. And it's not quite just a cone because there's a little bubble top, so it's kind of like a snow cone, and we've actually integrated something just like this before, but not in spherical coordinates. So it'll be exciting to compare this to the same technique we used previously, but to see how much easier it is once everything's in spherical coordinates. So maybe the first thing we should do is translate our equations into spherical coordinates. Remember that we have the equation that says x squared plus y squared plus z squared equals rho squared. So maybe first thing we do is take each of these equations and square both sides. So now we'll have z squared equals 3x squared plus 3y squared. And then the other equation would become z squared equals 4 minus x squared minus y squared. If I move the x squared and y squared to the other side, then I have x squared plus y squared plus z squared equals 2 squared. X squared plus y squared plus z squared, that's the same thing as rho squared. In spherical, we don't use a z, so instead of writing, rho squared is equal to, this is 2 squared, so that's going to be 2 squared. In other words, we have rho is equal to 2. So our sphere was able to be reduced down to a very simple equation, rho squared. Our cone, however, is going to take a little bit more work. So we have z squared, which we can replace with rho cosine phi, and that would be quantity squared. And then 3x squared plus 3y squared, I'm going to replace that with 3 times x squared plus y squared. I can simplify that a bit. Remember that we have equations that say x equals rho sine phi cosine theta, and y equals rho sine phi sine theta. So if we have x squared plus y squared, that's going to look like rho squared sine phi squared cosine squared plus sine squared theta. And we know cosine squared plus sine squared is equal to 1. So on the right-hand side, our 3x squared plus 3y squared, that's going to look like 3 times rho squared sine phi squared cosine squared plus sine squared theta. We know that cosine squared plus sine squared theta equals 1, so we're left with rho squared cosine phi squared on the left, and then 3 rho squared sine phi squared times 1 on the right. For our cone, we can divide off the rho squared because there's only one point on the cone where rho is equal to 0. Everywhere else, rho is not 0, so we can divide those off on both sides. And then we have cosine phi squared and sine phi squared, so we can square root both sides of our equation so that we have cosine phi is equal to root 3 sine phi. And then we need to think about our trig identities to help us solve this equation for phi. Remember that phi equals a constant will give us a cone in spherical coordinates, so we need to figure out what phi would make this true. And probably the best way to do that is to remember that tangent phi would be sine phi over cosine phi. So I can divide both sides of my equation by cosine phi to get 1 equals root 3 tangent phi. And then I'll divide through by my root 3 to get 1 over root 3 is equal to tangent phi. And then we just have to think about tangent inverse to get 1 over root 3. Using a calculator, you can find a decimal probably, but if you were to think about the known angles that we have, tangent theta equals 1 over root 3 comes from, sorry, not theta, but phi equals pi over 6. So the angle for phi in this cone is pi over 6. Phi equals pi over 6. Now, just take a second and appreciate how simple those two equations became. We had z equals square root 3 times the sum of x squared and y squared. Now that's just phi equals pi over 6. And then the hemisphere that came from the square root of 4 minus x squared minus y squared. Now that's just rho equals 2. So there's a huge benefit here to having our surfaces described in spherical coordinates. It greatly simplifies the equations we're working with. Now for space, I need to get rid of all this scratch work that we just did. Now when integrating in rectangular coordinates or cylindrical coordinates, we talked about determining the order of integration, making sure that we integrate in the right order so that we don't make our situation more complicated. And if we were dealing with a z variable, we would say integrate z first because the solid that we're looking at has a well-defined top, that's from the sphere, and a clearly defined bottom from the cone. But in spherical coordinates, the 3 variables that we have, none of them describe top and bottom. Instead, we're going to set up our triple integral more or less in any order that we want. And that's because if we look at the 3 variables, they're each going to be between constants. So rho gets to go from 0 all the way to 2 once it hits the sphere. Phi gets to go from 0 all the way to pi over 6 once it hits the cone. And then theta, if we were to think about the shadow of this solid, we could think about the xy plane or the r theta plane. And we would see that theta gets to go from 0 all the way to 2 pi. So setting up our solid, we can see that it's defined by rho going from 0 to 2, phi going from 0 to pi over 6, and then theta going from 0 to 2 pi. So we take those bounds, put them into our triple integral, and integrate like usual. Now the only thing to remember is that a triple integral over some solid in spherical coordinates, we need to take that dv and replace it with the volume increment in spherical, which was rho squared sine phi, and then all 3 of your variables. We have d rho, d phi, d theta. And it doesn't matter which order we integrate in this case because all 3 variables are squeezed between 2 constants. So let's go ahead and set it up. Let's just use this order, rho, phi, theta. So first we'll write in our rho squared sine phi, and we'll start with our d rho. Rho gets to go from 0 to 2, and then we'll put in our d phi. Phi gets to go from 0 to pi over 6, and then lastly d theta. Theta gets to go from 0 to 2 pi. And then we integrate just like we did on the last screen. Now, there are some symmetry arguments that could be made because our solid is very symmetrical. If you wanted to, you do not have to go all the way from 0 to 2 pi in theta. You could calculate half of it and then double the result that you get, but really that's not saving you much time. But if you're interested, you could think about some symmetry arguments. The last thing we need to talk about is how to translate an integral that's already set up in rectangular coordinates, for example, if we wanted to translate it to cylindrical coordinates, because we've seen that equations can be greatly simplified if we can just translate them into a different coordinate system. So the first thing that I like to do is to extract the solid that we're integrating over. So we're going to take out all of the bounds and write it a little more clearly. We can see that y goes from -1 to +1. X goes from 0 to the square root of 1 minus y squared. And then z goes from the square root, oh, nope, just kidding. The lower bound is x squared plus y squared. And the upper bound is the square root of x squared plus y squared. So first thing, extract all of the bounds that we're working with. Next, we're going to try and visualize what these variables construct. So remember when we first talked about triple integrals, we said you could do the first integral with respect to z and then look at the second two as some integral over the shadow. So let's try to construct our shadow. We know z is integrated first, which means our shadow should be in the xy plane. So looking at the xy equations, we can see that in the xy plane, we're looking at a circle. And if we aren't convinced of that, let's take the upper bound of the x inequality and look at it as if it were an equals sign, like a real equation. And we can manipulate this to see that it is a circle. It's a circle radius 1. And the y bounds are telling us to cover the entire circle. So if we're looking at a circle centered at the origin with radius 1, and we're told to do from y equals -1 all the way up to y equals +1, we know that our shadow is the entire circle in the xy plane. Next, we're going to look at the limits for z. So looking at the equations that we have for z, remember that z equals x squared plus y squared is an upward facing paraboloid. And then the equation z equals square root of x squared plus y squared, that's a cone. Both of these are centered at the origin, so we could stack them together. We can see that the bottom is our paraboloid and the top is our cone. So if we wanted to, we could translate everything into our cylindrical coordinate system, knowing that we're looking at a paraboloid, a cone, and then the shadow being a circle. We can set everything up in terms of cylindrical coordinates. So let's rewrite our paraboloid as an equation in cylindrical coordinates. The x squared plus y squared would be simply replaced with r squared. The cone would become the square root of r squared, so z would look like r. So our bottom is now r squared, our top is now r. We also need to convert the equation inside of the triple integral, x squared plus y squared plus z squared. Well, we can replace the x squared plus y squared with r squared. So now inside of our integral, we're looking at r squared plus z squared. So we can already set up that first inner integral. Z will go from r squared up to r, and we'll be integrating r squared plus z squared with respect to z first. Remember, cylindrical keeps the z variable. Next, we are going to replace our dx dy in the triple integral with r and theta, because in cylindrical coordinates, the xy plane is replaced with the r theta plane. We're still looking at a circle with radius 1, but when we describe that in polar coordinates, we say that r gets to go from 0 to 1, and theta gets to go from 0 to 2 pi. So we'll add those on. We'll do our r, dr, d theta. R values go from 0 to 1. Theta values go from 0 to 2 pi. Now, notice that in that polar area increment, we did have to add an extra factor of r, which needs to be in front of your dr differential. If you want, you can multiply it in right away. If you want to leave it until you integrate with respect to r, that's fine too. But either way, the triple integral that we started off with in rectangular coordinates has now been replaced with a triple integral in cylindrical coordinates. And the process we used was to first extract the bounds from the original integral, try and describe the shadow, translate all of your equations into cylindrical coordinates, and then rewrite your integral. And although we've already done a problem where we started off in rectangular coordinates and we translated into spherical coordinates, I figure it doesn't hurt to do one extra, so let's take a look at the following example. We're given a triple integral in rectangular coordinates. We're going to start off by extracting the bounds. We can see that y goes from 0 to 3. X goes from 0 to the square root of 9 minus y squared. And then z goes from the square root of x squared plus y squared up to the square root of 18 minus x squared minus y squared. All right, so we have our bounds. We know that z is integrated first, which means the shadow comes from the xy plane. So looking at our shadow in the xy plane, we can see, again, we have another circle. So the x equals square root 9 minus y squared. That becomes a circle with radius 3. And since y is going from 0 to 3, we can see that we're not talking about the whole circle, we're talking about just the top half. So when we translate that into spherical coordinates, we need to make sure that we don't accidentally include the entire circle for our shadow, it's just the top half. Now we need to look at the z variable and the bounds that it goes between. With enough practice, we start to recognize that z equals square root of x squared plus y squared is a cone. And if there's no constants in here, no multiples of a constant, our cone is phi equals pi over 4. And we've already worked on some of those, so if you're looking for more practice, you can go back to chapter 2 in our textbook. At the very end of chapter 2, there's lots of practice for translating between the different coordinate systems. And then looking at the upper bound for z, we can see that this is going to be a sphere. So we'll have something like z squared plus x squared plus y squared equals 18. X squared plus y squared plus z squared, that all becomes replaced with rho squared. So rho is equal to the square root of 18. And I believe that simplifies down to 3 root 2. Yeah, we can check that on a calculator if we're not sure. But we can see that we're looking at the bottom of our surface being defined by a cone, and the top of our curved surface being defined by a sphere. So we can set up our triple integral now that we have all of the pictures of the surface. Now, something to remember is that the shadow told us we're only looking at the top half of the circle. In other words, the top half of our shadow. And if we were to put our sphere and our cone together, so we've got our cone and we've got our sphere top, and then we look at our shadow in the xy plane, we're only looking at the positive y shadow. So we're really only looking at half of this cone. We're looking at the front half of the cone, and we're looking at the right side of the sphere. Or I guess it's the right side of both of them. We shouldn't say front for this one. And all of that is going to get factored in when we pick our theta. So we don't have to worry too much about that, but it will get factored in. So let's define our solid for rho, phi, theta. The smallest value of rho that we can have would be 0 because we are inside of the cone and the sphere. And if we were to think about a value for rho, it could go along the diagonal of the sphere, and then it would go, or sorry, the diagonal of the cone, stopping at the sphere, stopping at the sphere, stopping at the sphere. No matter where we're at, we're stopping at the sphere. So the largest value of rho then would be the radius of our sphere, and the smallest would be 0 since that's inside of our solid. For phi, we know that we're looking at phi starting from 0 and then coming all the way down to pi over 4. And then theta, if we're at the positive x-axis, that's theta equals 0. And then we're allowed to rotate all the way to the negative x-axis. So we're going to keep theta between 0 and pi over 2. Once again, all three of our variables are between constants, so the order of integration is not important here. But if you'd like, you can keep it in the same order that we've been in. So we'll set up our triple integral. Oh, one last thing, almost forgot. We have a function inside of our triple integral. We need to replace that with the equivalent in cylindrical coordinates. So if we have x times y times z, we need to replace those with the x equals rho sine phi cosine theta, y equals rho sine phi sine theta, and then z equals rho sine, just kidding, z equals rho cosine phi. So if we're multiplying all of these together, you can bet we're going to have rho cubed. We've got sine squared phi, cosine phi, and then cosine theta times sine theta. Now, notice we're not actually going to integrate this, so don't freak out, but we have this replacing the function that was x times y times z in rectangular. So that is going to be combined with the volume differential. Don't forget, dv is rho squared sine phi, and then d rho, d phi, d theta. So when we multiply our function times our volume differential, we would then have rho to the 5th power, sine phi to the 3rd power, cosine, phi, cosine, theta, sine, theta, and then d rho, d phi, d theta. And then we set up our bounds. Rho goes from 0 to 3 root 2. Phi goes from pi over 4, from 0 to pi over 4. And then theta goes from 0 to pi over 2. So anytime you need to convert between your coordinate systems, you're going to deconstruct the bounds that are given to you on the original integral, convert everything into the new coordinate system, including the function inside of your triple integral and including your volume increment. Make sure that you translate that appropriately. All right, guys, that's it. Good luck, and I'll see you on the other side.